Very good morning to all of you. I once again welcome you all to this current video lecture. In the last lecture, we started the second important spectroscopic technique, that is the infrared spectroscopy for the elucidation of the molecular structure. In that lecture, we completed the introduction, the principle of this particular IR spectroscopy, as well as one important point, that is the vibrational motion of a diatomic molecule. And in that, we derive or we take into consideration one equation for the calculation of energy of a molecule, that is the vibrational energy of a molecule in the unit of per centimeter, which is given by epsilon v in per centimeter is equal to v plus 1 by 2 into omega bar, where this v stands for vibrational quantum number and this omega bar is called as the fundamental vibrational frequency in the unit of CPS or in a hertz. So by using this equation now, we are going to study how to calculate the allowed vibrational energies in per centimeter for different values of vibrational quantum number. So for this purpose, we have to take the help of this equation. Now we are interested to calculate these energies. Now for this purpose, we have to consider this tabular data. So in the first column, vibrational quantum number is there. All possible values for this vibrational quantum numbers are there. In the second column, we have to calculate its allowed vibrational energy in per centimeter with the help of this equation. Now first of all, if we take into consideration vibrational quantum number v equal to 0, so when v equal to 0, if we substitute this value in this equation, that equation gives us the energy, that is a half omega bar. So we can say that whenever your molecule is present at this vibrational energy, the vibrational quantum number v equal to 0, at that time the energy of that molecule at that vibrational quantum number is equal to half omega bar. Now when vibrational quantum number is equal to 1, its energy comes out to be 3 by 2 omega bar. When it is a v equal to 2, its energy is a 5 by 2 omega bar. When v equal to 3, again if we substitute this in this equation, that value of vibrational energy comes out to be 7 by 2 omega bar. So in this way, we can say that if we go from v0 up to this v7, that is a different vibrational quantum number, if we substitute that values in this equation, we get the different type of allowed vibrational energies for a molecule, starting from half omega bar up to this 15 by 2 omega bar. So this is a different allowed vibrational energies in per centimeter for different values of vibrational quantum number. Now once we calculate this type of the allowed vibrational energies in per centimeter for a given value of this v, we are interested now to study the different allowed vibrational energies. We are interested in to study the different allowed vibrational energies, energy levels, what are the different possible transitions between them. So for this purpose, we have to consider now this figure. So in this figure, what you have to consider here? We have to consider here the respective energy of the different vibrational energy levels along versus this is the internuclear distance. So if we plot such a type of the graphical representation, that is internuclear distance versus this energy in a per centimeter, we get such a type of the nature for the different values of this vibrational quantum number. So this is nothing but a figure in which we get an idea regarding the allowed vibrational energy levels as well as the different possible transitions for the diatomic molecule which behaves as a simple harmonic oscillator. So what is there in this figure? So in this figure, the different allowed vibrational energy levels are there. The first vibrational energy level is v equal to 0. Second vibrational energy level is a v equal to 1, v equal to 2, v equal to 3, 4 and 5. So we consider here up to these 6 different vibrational energy level along with their vibrational quantum number. By considering these different energy levels, we have to consider their respective vibrational energies in a per centimeter. Suppose if we consider this first vibrational energy level with vibrational quantum number V equal to 0, it has the value of energy, that is a half omega bar. If that vibrational quantum number V equal to 1, its allowed vibrational energy in per centimeter is equal to 3 by 2 omega bar. So in this way, there are respective values of vibrational energy is there for a given vibrational energy level. The third thing is that we have to consider their allowed transitions. This type of the arrow. What is the meaning of this arrow? The arrow pointed from V equal to 0 to the V equal to 1. What is the meaning of this? The meaning of this is that this is the transition, this is the allowed transition for a simple diatomic molecule which goes from V equal to 0 to the V equal to 1. So we can say that this is called as the allowed transition. This is called as the allowed transition. And why this is allowed transition? Because if we take into consideration the selection rule for this particular infrared spectroscopy, that selection rule is equal to delta V is equal to plus minus 1. So this is a selection rule for this particular infrared spectroscopy. What is the meaning of this selection rule? If suppose there is a transition from V equal to 0 to the V equal to 1, and if we apply this selection rule to this transition, it is a difference is equal to plus 1, and that's how we can say that this transition is called as the allowed transition. This is allowed transition. Second thing is that if we consider the second transition, that is a V equal to 1 to the V equal to 2, again if we apply this selection rule, again this transition is called as the allowed transition. Same thing is there for transition from V equal to 2 to the V equal to 3. Same case is there for V equal to 3 to 4 and 4 to 5. So all these transitions are called as the allowed transitions by applying the given selection rule. Now this is called as the different allowed vibrational energy levels, their transition between them. And the next important part is, if we consider all these things together, what is the respective spectrum for this molecule? So the spectrum for this type of the diatomic molecule is like this. This type of the spectrum is obtained with some lines, with absorption lines can be takes place. So these absorption lines having this type of the frequency, that is a omega bar per centimeter, which is nothing but the fundamental vibrational frequency. So this figure includes the different allowed vibrational energy levels, their allowed transitions, as well as the spectrum for a diatomic molecule which behaves as a simple harmonic oscillator. So up to this study, we consider here how to calculate the allowed vibrational energies is per centimeter for the different values of V by using this equation. Nextly, we consider here the figure which gives us an idea regarding the different allowed vibrational energy levels, their energies, their allowed transitions, as well as the spectrum obtained for such a type of the simple harmonic oscillator. So this is nothing but the study regarding this type of the simple diatomic molecule. Now one thing we have to consider from this figure, that is, first of all, we consider here this table. In this table, the different allowed vibrational energies is there. So in this table, what happens? The first value, that when your quantum number V is equal to 0, when the quantum number V equal to 0, it has the energy of half omega bar. The same thing is there in this figure also. When we consider this allowed vibrational energy levels, when V equal to 0, its energy is a half omega bar. So we can say that even at the first, or even at the ground, or at the equilibrium position, when your molecule is at the V equal to 0 quantum number, at that time also its energy not equal to 0, but it is equal to the half omega bar. Then this energy for a molecule when V equal to 0 is called as the 0 point energy. This energy is called as 0 point energy. This energy is called as the 0 point energy. So what is the meaning of 0 point energy? The energy that is a half omega bar for a given molecule. When V equal to 0, then that energy is called as the 0 point energy. And what is the magnitude of this 0 point energy? It must be that 0 point energy must be that 0 point energy is equal to either half omega bar, or it may be half H into C omega bar in joules. So these are the two units for this. If it is a half omega bar, it is in a per centimeter. It is in a per centimeter. While if we have to consider this in a joules, that value is a half H into C into omega bar. It is in units of joules. So this is an important property for this simple diatomic molecule, that is called as the 0 point energy. The energy when your vibrational quantum number V is equal to 0. So up to this, we consider this different type of the allowed vibrational energy levels, their allowed transitions, the selection rule for this transition, the spectrum for this diatomic molecule, and important concept called as the 0 point energy. Now after the consideration of this type of the study, we have to consider now the next important part from this topic related to this infrared spectroscopy. That is, that important part or that important concept is there. That concept is called as the now vibration rotation spectra. What is the meaning of this vibration rotation spectra? So this is one important point from this chapter or from this infrared spectroscopy, vibration rotation spectra. Now what happens? We consider a diatomic molecule. We consider this diatomic molecule. This diatomic molecule can be considered to be as a harmonic oscillator, as considered to be the harmonic oscillator. So what happens whenever we consider this molecule as a harmonic oscillator? When this molecule is present in a gas phase, suppose when this molecule is present at the gas phase, suppose this is a molecule in gas phase, this molecule is there in a gas phase. So what happens whenever we apply the IR radiations, whenever we apply the infrared radiation, that is IR radiations are to be applied to this particular molecule in a gas phase. So what happens? We know that whenever the IR radiations can be absorbed by this type of the molecule in a gas phase, what happens? There is a change in terms of their vibrational energy levels can be takes place. Change in vibrational energy vibrational energy change can be takes place. Vibrational energy change can be takes place. Now as far as this vibrational energy change can be takes place, we know that along with this vibrational energy change, along with this type of the vibrational energy change takes place, we get a spectra. We get a spectra for this type of the vibrational energy change. We get a spectra. Suppose in this spectra, what happens? A very small lines is also occur. A small lines is also occur along with this type of the lines for vibrational energy change. So what happens? These closed space absorption lines, these closed space absorption lines is obtained due to the rotational energy change, due to the rotational energy change, due to the rotational energy change. Now the question arises, why we get such a type of the closed space lines along with this type of the lines due to vibrational energy change in a spectra? So what happens? Due to such a type of the closed space lines obtained in a spectra of a molecule, this type of the system is called as the rotating vibrator. This system is called as the rotating vibrator. or it may called as the rotating oscillator. It may called as the rotating oscillator. Now, what is the meaning of this rotating vibrator or rotating oscillator? First of all, we consider here the molecule irradiated with higher radiation. In this case, first of all, there is a change in vibrational energy can be takes place, and due to this energy, some lines can be obtained in a spectra. Now, if we observe this spectra has some closed space lines. Some closed space lines can be obtained in this spectra. Now, what is the importance of that lines? So that lines can be obtained due to the simultaneous change in rotational energy of a molecule, due to which we can say that that particular system is called as the rotating vibrator, or it may called as the rotating oscillator. Now, the question is, our question of discussion is that why this type of the energy change can be takes place along with this type of the vibrational energy change. Now, as far as the energy of radiations are considered, as far as energy of IR radiation is concerned, energy of IR radiation is concerned, it is greater than that of the microwave radiation. It is a more than that of the microwave radiation. So we can say that whenever these type of the IR radiations can be absorbed by a molecule, no doubt there is a change in vibrational energy can be takes place, but along with the or at the same time, due to the more energy of this IR radiation, they also changes its its rotational energy level also. That's why whenever we get the IR spectra of a molecule, it is nothing but a combination of change of vibrational energy as well as change of rotational energy. Therefore, we can say that pure vibrational spectra cannot be obtained. Therefore, we can say that pure vibrational spectra cannot be obtained. Pure vibration spectra cannot be obtained. And why this is so? Because in a spectra of a molecule, there is a combination of lines due to vibrational energy change as well as rotational energy change. Therefore, we can say that pure vibration spectra cannot be obtained. And under such situation, if we want to calculate the total energy of, this type of the rotating vibrator, then that energy is nothing but that is a epsilon v comma j. Epsilon v comma j. This v stands for vibrational quantum number and j stands for rotational quantum number. So under this situation, that energy is a combination of vibrational energy, that is epsilon vibrational energy plus rotational energy. So this is nothing but the combination of these two different forms of energy, that is the total energy of rotating vibrator is a combination of its vibrational energy as well as its rotational energy. So this is called as Born-Oppenheimer approximation. This is called as Born-Oppenheimer approximation. Born-Oppenheimer approximation. So what is the meaning of this Born-Oppenheimer approximation? If we want to calculate the total energy of rotating vibrator, it is nothing but the combination of its vibrational energy as well as its rotational energy change. So this approximation is nothing but the Born-Oppenheimer approximation, and this is nothing but the vibration rotation spectra. So what is the meaning of this vibration rotation spectra? Whenever a molecule get irradiated with IR radiation, it gives the lines due to the combination of the two energy changes simultaneously. One is the vibrational energy change and second is called as the rotational energy change. So the spectra obtained due to such a type of the energy changes is called as the vibration rotation spectra, and that molecule is called as the rotating vibrator, or it may be called as the rotating oscillator. And why this type of the lines can be obtained? This is due to the energy of IR radiation is more than that of the microwave radiations. So whenever these IR radiations can be absorbed by a molecule, it carry out the two type of the changes in terms of its vibrational energy as well as rotational energy of a molecule. So we cannot get always a pure vibration spectra, but we get a combined spectra. So if we want to calculate the energy for such a type of the system, then it is nothing but the combination of its vibrational energy as well as its rotational energy, and this is nothing but the Born-Oppenheimer approximation. So in today's lecture, we consider the different aspects regarding this IR spectroscopy. In the first part, we consider here how to calculate the allowed vibration energies in per centimeter for different values of vibrational quantum number. In the second part, we consider the different type of the allowed vibrational energy levels, its allowed transitions and its spectrum. And at the last part, we consider just now the important point, that is a vibration rotation spectra of a molecule. So this is regarding the second important spectroscopic technique, that is a infrared spectroscopy. Now the remaining points from the chapter we will cover in a next lecture. So with this, today I stop here. Thank you so much.